Hello everyone, welcome to week 3 of NET 424 Information Storage. Let's go ahead and jump into what we'll talk about today. We'll be talking about the course overview and expectations. Excuse me, taking a drink of water there. Submissions and requirements, tips and insights. We'll talk about the week 3 assignments, which is the week 3 discussion board posts, assignment, and assessment. Then you'll be talking, every week you're going to have daily checkpoints, you're going to have discussion, you're going to have an assignment, and you're going to have assessment, and also you'll have the live lecture quiz, something you all should be pretty familiar with at this point, seeing that we've been doing this throughout the class pretty much. And then in week 4, you'll have a career integration quiz. Then you have daily checkpoints, which are short tasks for daily participation, 10 to 15-minute assignments. They're for track active engagement in the course. And again, you're required to do 4 per week. Everything that you do extra than the 4 are counted as extra credit at the end of the class or added to your grade. So if you do 7, those 3 extra ones will be added. Daily checkpoints are due every 24 hours. There's no late submissions for them. Assignments and assessments are due Sunday at 11:59 p.m. Mountain Standard Time. Your discussion board post, initial post is 150 word main post due on Wednesday, which was yesterday at 11:59 p.m. Mountain Standard Time. The responding to 2 peers is due Sunday at 11:59 p.m. Mountain Standard Time. How to get help if you need to get help. You can call and email your instructor, which is me. You can attend the required live sessions, or you can watch the recording. There's student tutor help. You can reach out to them. His name is Richard Guy. There's a flyer that is actually on the announcement section. And let's go ahead and continue on. So for the week 3 discussion, it says read the article below and discuss how, and we'll cover this by the way, but read the article below and discuss how breaking traditional RAID concepts help big data deal with ever-growing needs of its storage system. Again, you have one main post of 150 words with one citation or reference, and respond to 2 peers with 50 plus words is due by Sunday at 11:59 p.m. Mountain Standard Time. The week 1 assignment, you're going to be doing log into the VMware training website and complete the lab on vSAN 6.6. Now, in the instructions, it's labeled differently, but this is the one that you have to do right here, the HOL-2108-01. And again, you're going to take a screenshot, and that is what you're going to go ahead and submit there. And then for the assessment, you're going to have a quiz again for the assessment. So let's go ahead and look into the assignments that you will be doing this week. All right, so let's look at the week 3 discussion. So the week 3 discussion, again, the initial post is due Wednesday at 11:59 p.m. Mountain Standard Time for a total of the initial post is due Wednesday at 11:59 p.m. Mountain Standard Time. Responding to 2 peers is due Sunday at 11:59 p.m. Mountain Standard Time for a total of 60 points. The career relevancy section says you'll be covering the understanding how enterprise data storage providers such as Google, Amazon Web Service, and Microsoft Azure can help you choose more efficient methods and technologies in your own data storage architect. AWS and Microsoft, I mean, they're all 3 very popular. Those are very 3 popular top of the line. Azure is a big one. You see a lot of positions being posted, cybersecurity or information technology positions for Microsoft Azure and Amazon Web Services, definitely. The background section says data and storage expansion is a challenging task for cloud service providers and data center managers. New technologies can be leveraged to implement storage backends, but when you have as much data growth as Google, sometimes you need to think outside the box. The Google file system uses many architecture concepts as RAID, but pushes that up further into the OSI reference model by using software-defined storage, meaning um, uh, uh, um, the normal RAID is used hardware, which is lower on the OSI model. Have you ever wondered how all the cloud storage was being presented to end users? A lot of that is proprietary. meaning that they're just going to kind of hide it. It's their own data, but it's rooted in the basic concept of RAID, distributed file systems and clustering. If we dig a little, we can find that Google Cloud Service offers some details that gives us some insight into the Google file system. That says Google hasn't done anything unique with the platform that other people have not already. They just put together and scaled it to an unprecedented heights. GFS doesn't use any specific RAID controllers, fiber channel, iSCSI, HBAs, FC, or SCSI disks, dual porting, or any other costly hardware we expect in a wide awake data center. And yet it all works and works very well. But having a software data manager take care of the block storage and having multiple replication points, GFS is not bound by RAID structures and configuration. Google does use clustering and data chunking out their disks with redundant copies at the block layer instead of using predefined structures on RAID arrays. If you don't have to perform all this RAID and storage pool setup beforehand, you can easily cut down on the time to provision storage on demand. Need more space? Add more disks and register them with data handlers. So it says for the prompts is read the article below how breaking the traditional RAID concept helps big data deal with ever-growing need of storage systems. Your initial and post reply should develop a group understanding of this topic. Um, Challenge each other, build on each other, and always be respectful. So let's take a look at this first article here, or excuse me, this article right here. Sorry. Let me see here. All right, looks like this thing is not wanting to open for me. It usually opens. Let me try something else here. Let me try something. I don't know what's going on with the link for me now. There we go. Maybe the site's down now. I hope it's not down. There we go. I just wanted to make sure. Hold on 1 second here. So it says the Google File System Eval Part 1. This is here. We can go ahead and, yeah, let's just read through this together here. And then I'll kind of give you my insight. So it says the GSF fundamental paradigm shift or one-off oddity. It says, as regular readers know, I believe that the current model of enterprise storage is badly broken. While I see something that blows that model away, like to learn more. In particular, I assess the marketability of the innovation. So cool technology like GFS or backup compression makes me wonder if and how customers would buy it. So they're basically saying that they like to learn about new technology, but they have to learn about, like, is it like marketable? Like, is it a cost? Is it affordable? Would a company or organization get a return on investment if they were to invest in something like GFS? This article offers over 1,000-foot view of GFS by way assessing its commercial viability. If you want a technical article about GFS, I can only recommend the Google File System article, from which this article draws heavily. The Wikipedia article, oddly, isn't very good on GFS. And if you don't have a BC or CS or better, you'll find the Joe Walt slog probably worthwhile, good for temporary relief of insomnia. So this guy has a nice little tone to it, you know? So here. So it says here for Google from space, it says GFS is one of the key technologies that enabled the most powerful general purpose cluster in history. While most IT folks lose sleep over keeping the Exchange server backed up for a couple thousand users, Google's infrastructure both supports massive user population and regular rollout of compute and data intensive applications that would leave most IT obstacles gibbering in fear. How do they do it? So basically, they're saying, well, most people are worried about like Exchange server, which is an email server, backing that up. GFS can do that for like whole networks. Partially, they are smarter than you. Google employs hundreds of comp sci PhDs, as well as many more hundreds of really smart people, partly in their history and impoverished PhD candidates can't afford fancy hardware to build their toys, so they started cheap and got cheaper. And finally, really smart and really poor, they rethought the whole IT infrastructure paradigm. The big insight: rather than build availability into every IT element at great cost, build availability around every element at low cost, which totally changes the economics of IT. Just as the mini computer in the 70s, the PC in the 80s, and the land in the 90s all did, only more so. When processing bandwidth and storage are cheap, you can afford to spend lots of cycles on what IBM calls automatic computing. When the system properly architected and cheap to build out, it scales both operationally and economically. All that said, Google hasn't done anything unique with their platform that other people haven't already. They put it together and scaled it to unprecedented heights. Note to CIOs: this is going to take users long to notice that Google could do stuff and you can't. Your life isn't going to get easier. So this article has really great humor to it that I like a lot. So then it says here next, it says GFS from low Earth orbit. Despite the name GFS, not to be confused, although how exactly I don't know, with Sinesta's GFS, which I don't even know what that is, to be honest. Hold on one second, please. It says maybe we should call it GoofS. It's just not a file system. Um, it's just not a file system. It also maintains data redundancy, supports low cost snapshots, and in addition to normal create, delete, open, close, read, write operations, um, also offers a record append operation. The record append operation reflects on the unique nature of the Google workload. Fed by hundreds of web crawling bots, Google's data is consistently upgraded with large sequential writes. Rather than synchronize and coordinate the overwriting of existing data, it's much cheaper to simply append new data to existing data, meaning they just keep adding more to the space. Um, Another feature of the Google workload is that most consist of two kinds of reads: large streaming reads and small random reads. As large reads and writes are so common, GFS is optimized for substantial bandwidth rather than low latency on IOPS. As multi-gigabyte files are the common case, GFS is optimized for handling a few million files. So doing the math, a single GFS should be able to handle a few petabytes of active data. All this build on very cheap components whose frequently failure give the size of cluster as expected. The system monitors itself and detects, tolerates, and recovers quickly from component failures, include risk, disk, network, and server failures. So it's almost in RAID that it has that fault tolerance. GPS from a SR71 Blackbird. GFS cluster consists of single master and multiple chunk servers and is assessed by multiple clients. Each of these is typically dirt cheap Linux box, initially dual 2 gigahertz Xeons with 2 GB RAM and 8 GB of disk. Files are divided into chunks, each identified by a unique 64-bit handle, and are stored on local systems as Linux files. Each chunk is replicated at least once on another server, which is that data redundancy, and the default is 3 copies of every chunk. Take that RAID 6 fanboys, saying it's doing better than RAID 6. The chunks are big, like the files they make up. 64 megabytes is a standard chunk size, which is, you know, pretty sizable. The chunk servers don't cache file data since the chunks are stored locally, and the Linux buffer cache frequently access data in the memory. If, like me, you thought the bottleneck / SPOF, when you saw the single master, you would, like me, have been several steps behind the architect. The master only tells clients and tiny multibyte messages which chunk server has needed chunks. Clients then interact directly with chunk servers for most subsequent operations. Now, Grok, one of the big advantages of a large chunk size, clients don't need much interaction with masters to gather access to a lot of data. This covers the bottleneck program. Bottleneck meaning you have a lot of data coming in, but you have a small bandwidth for it to come through. But what about SPOF, single point of failure problems? We know that data is usually copied 3 times. When disk is really cheap, you can afford that. But what about the all important metadata that keeps track of where those chunks are? The master stores and memory for speed 3 types of metadata: file and chunk names, mapping from files to chunks, and locations of each chunk space. So since they store it in memory, it's going to be quicker. It's almost like an SSD drive and that it stores in memory. So if the master crashes, the data has to be replaced pronto. The first two, namespace and mapping, are kept persistent by a log stored of the master's local disk and replicated on remote machines. The log is checkpoint frequently for fast recovery if a new master is needed. How fast? Read startup almost instantly thanks to shadow masters who stay current with the master in the background. Write pause for about 30 to 60 seconds with the new master and chunk server make nice. Many RAID arrays recover no faster. The last type of metadata, replication locations, is stored on a file chunk server and copied on nearby machines and given to the master at startup or when a chunk server enters the cluster. Since the master controls the chunk placement, it is able to keep itself up to date as new chunks get written. The master also keeps track of health of the cluster through handshaking with all chunk servers. Data corruption is detected through checksumming. Even so, data may still get pooched, thus the GFS reliance on appending writes instead of overwrites. Combined with frequent checkpoints, snapshots, and replicas, the chance of data loss is very low, results in data unavailability or data not corruption. One second here, let me get a drink of water, please. Sorry. GSF RAID. They don't call it that, but StorageMojo.com cares about storage. And I find a part particularly interesting. GFS doesn't use any RAID controllers, fiber channels, iSCSI, HBAs, FC, or SCCI disks, dual porting, or any other cost bling we expect in a wide awake data center, and yet it all works very well. um, to take replica creation, or what you and I would call mirroring. Basically, mirroring is where we talked about this before, where you copy one drive and then you copy on another. All the servers in the cluster are connected over a full duplex, switched Ethernet fabric with pipeline data transfers. This means that as soon as the new chunk starts arriving, the chunk server can begin making replicas at a full network bandwidth of 12 megabytes per second without reducing the incoming data rate. As soon as the first replica chunk server has received some data, it repeats the process so that the two replicas are completed soon after the first chunk write finishes. In addition to creating replicas quickly, the master replica placement rules also spread them across machines and across racks to limit the chance of data availability due to the power or network switch loss. Um, Pooling and balancing, storage virtualization may be on the downside of the hype cycle. And looking at GFS, you can see what simple virtualization looks like when built into the file system. Instead of complex software layer to pool all the blocks across RAID arrays, GFS masters place new replicas on chunk servers with below average disk utilization. So over time, utilization equalizes across servers without any tricky and expensive software. The master also rebalances replicas periodically. Look at disk space utilization, load balancing. This process also keeps a new chunk server from being swamped the moment it joins the cluster. The master allocates data to it gradually. The master also moves chunks from chunk servers without above average disk utilization to equalize usage. Storage capacity is reclaimed slowly rather than eager deletion. The master lets old chunks hang around for a few days and reclaims storage in batches done in the background when the master isn't too busy and minimize the impact of the clusters. Uh, in addition, um, since the chunks are renamed rather than detected, the system provides another line of defense against accidental loss. So let's go ahead and then talk about our week 3 assignment. So the week 3 assignment, the career is due Saturday or Sunday at 11:59 p.m. Mountain Standard Time, and that's due for 100 points. The career relevancy section says access control and identity management. Uh, Integration into file system is important to access control and security. By having object and subject control mechanisms, we can maintain security boundaries, and our system will implement what security engineers refer to as defense in depth. For those of you who don't know, defense in depth is where you have multiple defensive measures for if one fails, another will kind of like pick up the slack and cover and protect the data where before it couldn't. Uh, Network access control list, file and folder size control list are two ways in which we can restrict access to file system data. Basically, they're talking about permissions, files, and folder access control lists. Those are like permissions that you grant, like NFTS permissions, network file system permissions that you probably learned about and if you took a server class. Background, access control and identity management, integration to file system is important to access control and security. Access control means you're basically able to control who's able to access, and then identity management means you're able to verify people's identity and ensure that they are who they say they are, so then they can get the proper access. By having object and subject control mechanisms, we can maintain security boundaries, and our systems will implement what security engineers refer to as defense in depth. Um, Network access control list, file and folder access control list are two ways in which you can restrict file system data. Again, the prompt says there are many competing technologies for allowing storage access over TCP. Explore the benefits of software-defined storage and complete modules 1 and 2 in the VMware SAN lab. So it says here, log into VMware and complete the lab on VAN version 6.6, upload an image. One thing, and again, I want to come back here. This video will show you how to sign up for it, but this is not the one right here that you want to do. The one that you want to do is, let me pull it up here on my screen so that you guys can see, is right here. The HOL 210, oops, sorry, the HOL 2108 01 HCI. And again, I sent that out in an announcement, so everyone should have probably gotten it at this point. Let's go back to where we were. All right. And then let's talk about the assessment. So the assessment is 180 points. You're gonna have or excuse me, 180 minutes. You're gonna have it's due Sunday at 11:59 p.m. Mountain Standard Time. You're gonna have 5 questions for a total of 50 points. And you're gonna go ahead and again, you're gonna read these little like kind of articles here, and then you're gonna answer the question there. And again, that's for a total of 50 points. So before we do our next PowerPoint presentation, we're going to take a 5-minute break, and then we're going to come back here and we will take it from there. So I will see you guys in 5 minutes. All right, so let's go ahead and continue on with where we left off. We're going to be starting. So describe the chapter goals is going to be describe the distinguished characteristics of primary and secondary storage. Describe the devices used to implement primary storage. Describe the memory allocation schemes. Compare and contrast secondary storage technology alternatives. Then we are going to talk and describe factors that determine storage device performance. Choose appropriate secondary storage technologies and devices. Explore storage devices and their technologies. Uh, Outline characteristics common to all storage devices. And explain the technology strengths and weaknesses of primary storage and secondary storage. So storage types, you have primary storage, which is memory or RAM, holds instructions and data for currently executing programs. Volatile requires electronicity to maintain data. Then you have secondary storage, which is electromagnetic or optical devices, which is non-volatile storage devices, which large capabilities. Like memory and RAM, basically for those of you who, and I assume that everyone here took introduction to operating systems, but basically how it works in a nutshell is your memory or your RAM processes instructions that your CPU sends out. So like a application runs, CPU starts processing it and puts instructions on memory or RAM, and then once power is gone, like you power down a system, all that stuff is off the memory or RAM. Or once it's done running the commands, where with electronic electromagnetic or optical devices, they're basically non-volatile, meaning that they'll stay there. Now there is also uh, memory type of drives, solid state drives, that is also non-volatile. Hold on a second. Storage device components. Storage devices are comprised of storage medium, which is, for example, like the memory or the platters. Read-write mechanism, such as a needle. Device controller, which is the interface between the storage device and the system bus. Here's some storage device characteristics. You have where speed, the description is time required to read or write a bit, byte, or larger unit of data. And the cost increases as speed increases. Volatility, ability to hold data indefinitely, particularly in the absence of external power. And the cost is for devices or of similar type. Cost decreased as volatility increases. Access method can be serial, random, or parallel. Parallel devices are also serial or random access. Cost is serial is the least expensive, random is more expensive than serial. Parallel access is more expensive than non-parallel access. Portability, ability to easily remove and reinstall the storage media from the device or the device from the computer. For devices of similar type, portability, increased cost if all other characteristics are held constant. Capacity is maximum data storage held by the device or storage medium. and can usually increase in direct proportion or capability. Speed of primary storage, RAM, directly impacts performance of the entire system. RAM extends the limited capacity of CPU registers, but basically it's kind of that brain versus memory kind of explanation. The more RAM that a system has, the CPU has more capabilities that it can do. The CPU continuously moves data instructions between registers and RAM. If a read write to RAM takes more than one CPU cycle, then the CPU must wait for information. So that means if you have more RAM, that's less cycles that you have to worry about. RAM is faster than secondary storage by a factor of 10 to the fifth power or more. It's kind of not saying RAM is as fast as a solid state drive, but that's kind of why solid state drives are faster, because they run off of memory. Speed is also an issue for secondary storage called access time or seek time. Access time is defined as time to complete one read or write operation. Access time for disk or tape storage can vary depending on location of information. Therefore, access time is expressed as an average. And that's also kind of what we're talking about when it came to solid state drives, or between solid state drives and hard drives, magnetic platters, is that you might even want to mix the two. You might even want to have solid state drives that have your data that's most commonly used, that people commonly access, so that it can be quicker and access quicker, and the data that's not used as much be on a platter drive. And then have where, you have, there's a lot of programs that'll do this, where say, oh, this data now that was considered cold, that's not used as much, we'll move it to, it's being used now, so let's move it to the solid state drive. And oh, I see that this hot data is no longer hot, let me move it to the platter drive. Access time, primary storage expressed in nanoseconds, billionth of a second. Secondary storage expressed in milliseconds, thousandths of a second. Data transfer rate is a complete measure of data access. Data access speed consists of access time and the unit of data transferred to from the storage device. Access time plus how much data is transferred. Data transfer unit for primary storage is based on the word size. Usually it's 32 bits. Data transfer unit, amount of data moved at a time. For secondary storage, varies depending on the device. Unit is called a block, so it's a block of unit. Block size is stated in bytes. A sector is data transfer unit for magnetic and optical drives. You have different sectors of a magnetic hard drive. Common size is 512. Then you have the data transfer rate expressed in terms of bytes in second. Access time combined with data transfer unit. And then they have data transfer rate describes how much data can be transferred between devices over a period of time. Then volatility is volatile. Storage device is volatile if it cannot reliably hold data for long periods of time. Non-volatile storage device is non-volatile if it can reliably store data for long periods of time. A computer system needs a combination of volatile and non-volatile storage devices. That's just what you need. You need to have data that you store in there. That's why you have computers, and you need random access memory to be able to, so your CPU can run. Access method, physical structure of stored devices, read-write mechanism, determine the way that data can be accessed. You have serial access, random access, and parallel access. Storage stores and receives data items in a linear or sequential order. It's the slowest access method. Tape typically used for backup purposes. Tapes are really popular at this point. Random access, also called direct access device, can directly access data stored on the device. All primary storage and disk storage devices are direct access. You have parallel access with multiple read-write heads, can simultaneously access more than one storage location. Then you have portability. Data can be made portable by storing it on a removable storage medium or device. Portable device typically has slower access speeds than permanently installed devices and those with non-volatile memory. Cost and capacity, increase in speed, permanence, or portability generally comes at increased cost if all other factors are held constant. Here's some storage device characteristics here. It's a comparison of storage devices in terms of cost and access speed. So you have access speed is high, the cost per bit is higher, and the capacity is low. So if you have low speed, low cost, you can have higher capacity. So you see an example here of primary storage. You have CPU registers, CPU cache, and random access memory. Access speed is high, the cost per bit is high, but it has low capacity. But then when you have like a magnetic disk, optical disk, or magnetic tape, which is secondary storage that has low access speed, a lower cost of per bit, but it has a high capacity, meaning it can store more. And you can even throw in the middle of this like SSD drives, where it kind of has that access speed, cost per bit, but at a lower capacity than magnetic disks. Primary storage devices, you have random access memory. RAM is a generic term for storage device that microchip implementation using semiconductors, ability to read and write with equal speed, random access to stored bytes, words, or larger data units. You have critical performance characteristics, access speed, data transfer unit size, and must closely match CPU speed and word size to avoid wait states. Storing electronic signals directly by devices such as batteries and capacitors, trade off between access speed and volatility. Indirectly uses energy to alter the state of the device. Inverse processes regenerates equivalent electronic magnetic signal. And modern computers use memory implemented with semiconductors, RAM, and NVM. Random access memory characteristics, microchip implementing using semiconductors, ability to read and write with equal speed, random access to stored bytes, words, or larger data units. Hold on one second here. The random access memory characteristics, microchip implementation using semiconductors, ability to read and write with equal speed, and random access to stored bytes, words, or larger data units. You have static RAM, which is SRAM, implemented with transistors, requires a continuous supply of electricity to preserve data. Then you have dynamic RAM, uses transistors and capacitors, and requires a fresh infusion of power thousands of times per second. Then each refresh operation is called the refresh cycle. To bridge performance gap between memory and microprocessors, read-ahead memory access, synchronous read operations, and on-chip memory caches. Then you have non-volatile memory, random access memory with long-term or permanent data retention, usually relegated to specialized roles and secondary storage, slower write speeds, and limited number of rewrites. Generations of devices such as ROM, EPROM, and EEPROM. Let's see, so long we still got left. Let's go ahead and we'll take our next 5-minute break, and then we'll meet up here. All right, let's go ahead. And what we are going to do now is, hold on one second here. we're gonna jump into a video here that we're gonna show that is going to cover introduction of file sharing. So let's go ahead and watch this. All right, folks. So that is the class for today. If anyone has issues, please feel free to email me. Until then, I will see you next time. Thank you.